Hello, college algebra students and pre-calculus students, and welcome to the video on inverse functions. In this video, we're going to define inverse functions. We're going to find their values from a set or a graph. We're going to find the formulas for them algebraically, and finally, we're going to verify that functions are inverses. Let's go ahead and get started. So let's start with the definition. If we have a function f of x, then f inverse of x is inverse function of f of x. So this notation right here is not an exponent. It is designating f inverse of x. And what it means is that f inverse of y equals x for all values x and y. So if f of x takes x to y, then f inverse takes y back to x. So for example, if f of 1 is 3, then f inverse of 3 is 1. So those guys go hand in hand. So therefore, if the point 1, 3 is on the graph of f of x, like f of 1 is 3, then on the graph of f inverse, you would have the point 3, 1. Let's go ahead and do this from a set to get a feel for this. So if we have the function get defined by a set as below, if we want to find the inverse set, we would make sure that we match all the pairs, but in reverse order. So in the original function, 0 goes to 1. So in our inverse function, 1 goes to 0. 2 goes to negative 3. So our inverse function, 3 goes to 2. 9 goes to 4. And finally, negative 4 goes to 12. So this is our inverse function. So you can see that the domain of the original function becomes the range of the inverse function. So in the original function f, my domain was 0, 2, 4, and 12. And my range was 1, negative 3, 9, and negative 4. In my inverse function, I would have the exact opposite, swapped domain and range. So my domain for my inverse function is 1, negative 3, 9, and negative 4. And my range is 0, 2, 4, and 12. All right, let's keep going on with inverse functions. Let's think about inverses from a graph. Let's make this a little bit. So here is our function, and we're going to call it p of g. And so our independent variable in this example is g, apparently. I don't know why I picked that. And our dependent variable is p of g. So if we wanted to find the values below, we're interested in some values for p inverse. So to help me figure these out, I'm going to zoom out just a little bit farther. So to help me figure these out, it helps me to just first find a few values of p, just to get a feel for this function. So off to the side here, I'm just going to fill up a little table with g and p of g. And looking at some values. So just thinking about this function that's being graphed. So if I take an input of negative 3, let me just erase this right here. This is messing with my thing. If I take an input of negative 3, it has an output of, well, it looks like about negative 6, negative 7. And if I had an input, let's do 0 just for a couple more values. If I put an input of 0, I get 2 out. And if I put an input of 4, I get 4 out. So those are just some values that map g to p of g. So what it wants to know is what would be the inverse function evaluated at 3. So if I'm trying to figure this out, my original question, I'm really asking p of what equals 3, because that would be the point we don't know, question mark 3. So when I do my inverse function, this would be 3 something that we don't know, and that would tell me that p inverse of 3 is that value. So what I need to do is I need to figure out what input has an output of 3 in my original function. So let's look. Here's 3. If I come over here, it hits right about at 2. So I would say in my original function, p of 2 is 3. So that is the point 2, 3 on my graph of p. So if I go to p inverse, it would go 3 to 2. So that tells me p inverse of 3 is equal to 2. All right, so following in that same logic, I would like you to pause the video and try to find p inverse of -1. All right, were you able to find it? So what we're asking for now is we really want to know, for my original function p, what input has an output of -1? Well, let's go to -1. It's right about here. We trace over, and it is -1. It looks like the point -1, -1. So that means that the point -1 is on the graph, which transfers to -1, -1. So P inverse of -1 is -1. All right, let's do the last problem here to working with the graph. This is asking what input value has an output of -2 in the inverse function. So let's work backward on this. For my inverse function P inverse, I want to know what value has an output of -2. So if I transfer that to P, that would mean if I have an input of -2, what is my output? So I go to -2, my output is -4. Working backwards, this tells me that P inverse of -4 would be -2. So you just have to be able to work forward and backward with these inverse functions. All right, let's think about inverses from an equation. I'm going to give you a nice algorithm that you've probably seen in other places in just a bit, but let's just talk it through for a minute. Here's my function f of x. And this function takes an input, multiplies it by 3, and adds 1. So if I put in any value for x, I would multiply by 3 first. So this is what f does. I would multiply by 3, and then I would add 1. So if I wanted to do the opposite of those things, if I was thinking about how to, the opposite, undoing all those things, well, to undo all those things, the first thing I would do would be subtract 1, right? That would be the opposite of adding 1. And I would do it first because I added 1 last. So if I wanted to get back to my value, I would subtract 1, and then I would divide by 3. Those are my opposites, and that's what my inverse function should do. So just in words, if my original function multiplies by 3 and then adds 1, my inverse function, backtrack that, should subtract 1 and then divide by 3 to get back to the original value. So you can kind of think through this just by looking at what the function does. And so I can guess that my inverse function of x should be take my value, subtract 1, and then divide everything by 3. So that's my guess for my inverse function. Luckily, we have a nice algorithm that'll help you, but it's important to just think through what exactly this inverse function is doing. Oops. So let's try and do another example of this. And we're not going to talk through it this time. We will think about it before we begin. We're going to use the algorithm. So this new function f of x multiplies by 2 and subtracts 5. So in our head, we kind of know what it should do. But we're going to go ahead and use the algorithm for this one because these do get a little bit complicated. So what the algorithm does to help you figure out the inverse function, the first thing you do is you're going to substitute y in for f of x. And the reason we do this is we don't usually work algebraically with the notation f of x because it kind of looks like multiplication, and we don't want to get confused. So the first thing we're going to do with our example is write y equals 2x minus 5 instead of using that f notation. And then the next thing we're going to do is we're going to switch x and y. And this is our inverse, right? Switch our x and y in our equation. So we're going to come over here and we're going to write x equals 2y minus 5. We're going to switch roles. And the next thing we do is we just solve this new equation for y. So if I look at this equation, I want to solve it for y. Well, the first thing I'm going to do is add 5 because that's what my undo operations tell me to do. So x plus 5 equals 2y. And then to completely isolate y, I'm going to divide both sides by 2. And this gives me y equals x plus 5 over 2. And then the last step is to use the notation f inverse for y. So replace y with f inverse. So my inverse equation is f inverse of x equals x plus 5 over 2. So that's the algorithmic method for finding the inverse. I think it'd be really fun right now. Let's go up and pause the video, go back and do the problem we just did, the one we just thought through, and try this method and see if it works for you. While you do that, I'm going to erase and we're going to try it with the next problem. All right, did you give it a try? So we started with f of x equals 3x plus 1. This was the one we just talked through. We didn't use the algorithm. Let's try the algorithm. We're going to write y for f of x, so y equals 3x plus 1. We're going to switch x and y, and we're going to solve for y. So to solve this equation for y, we first subtract the 1. X minus 1 equals 3y, and then we would divide by 3. And finally, we'd write this as f inverse of x. And that worked out great. That's exactly what we got when we just thought through it. I just want to point out one quick notation thing here too. I'm just writing the f inverse on the right-hand side because that's where the y ended up. You can rewrite this as f inverse of x equals x minus 1 over 3. That's totally fine. In fact, I kind of prefer to have the function notation on the left. All right. So we went through that. There's the steps again written out more carefully. Switch the input and output variable, solve for the output variable, change the output variable to inverse notation. So let's try one more of these guys with a little bit harder algebra here. So let's give a try f of x as 2x cubed plus 1. Let's find f inverse of x. So y equals 2x cubed plus 1 is our first step. Now we're going to solve for y. Y minus, oops, no, that's not the right next step. You guys let me mess around here. Okay, what's the correct next step? All right, let's try this with a little bit harder example. F of x equals 2x cubed plus 1. We're going to try and find f inverse of x. So our first step is to write the output variable as y. So y equals 2x cubed plus 1. And then we're going to switch our x and y. X equals 2y cubed plus 1. And now we solve for y. X minus 1 equals 2y cubed. Divide by 2. We have x minus 1 over 2 equals y cubed. Keep going. How do we undo cube? Well, we take a cube root. So we take the cube root of each side, and that gives us y equals the cube root of x minus 1 over 2. So that is our inverse function. So let's rewrite that. F inverse of x equals the cube root of x minus 1 over 2. All righty. So let's think about this a little bit more. Now we can find inverse functions in tables and graphs and algebraic formulas. Let's think about all functions have inverses. For this example, let's think about the nice function f of x equals x squared. If we put in f of negative 2, let's go ahead and practice our function notation. We would find f of negative 2 equals negative 2 squared, which is 4. And if we found f of 2, we would put 2 squared, which is also 4. So f of negative 2 and f of 2 both map to 4. So if we were thinking about the inverse function, so this takes negative 2 to 4, and this takes 2 to 4. If we were thinking about the inverse function and we put in 4, do we go back to 2 or do we go back to negative 2? So is this 2 or is this negative 2? And the question is, we don't know because this isn't a function, right? If we have an input that has two different outputs, so 4 could go to 2 half the time or negative 2 the other half, that does not make a function. That's not a function anymore. So our inverse function isn't a function. All right, so this means that x squared doesn't have an inverse function on its whole domain. So what kind of functions are we interested in? Well, we're interested in functions that are called one-to-one. And this means not only, like we need for the function definition, every input has exactly one output, but also we need every output to only have one input. So that's what I mean by one-to-one. There's one input for each output and one output for each input. Both of those things have to hold true to have an inverse function. X squared is still a function. It takes the same input to exactly the same output every single time. It just doesn't have an inverse on its whole domain. There's a nice handy way to tell if a function is one-to-one graphically. And that's using the horizontal line test. So it's sort of like the vertical line test, but for one-to-one functions. So for example, here's our first graph. This is x squared. You can draw a vertical line that touches the graph more than once. Did I say vertical? You can draw a horizontal line that touches the graph more than once. So this output of 2 has 2 different input values. Actually, this isn't even x squared, is it? It's a parabola. You get the idea. Oh, no, it is. This is 2. Okay. There is a really great test we can use to decide if a function is one-to-one, and that's called the horizontal line test. Very similar to the vertical line test. Vertical line tests decide if something is a function. Horizontal line tests decide if a function is a one-to-one. So a function is one-to-one if you cannot draw a horizontal line that touches a graph in more than one location. So for our first example, we're looking at x squared. This is just f of x equals x squared. We already know it's not one-to-one. And if we just look even here at our value, we draw this horizontal line right here, we can see that the input of 2 has an output of 4, and the input of -2 also has an output of 4. So that's not going to pass the horizontal line test, and that function is not one-to-one. You're not going to be able to have any repeated outputs on a one-to-one function. If we look at this nice exponential growth curve over here, we can see this does pass the horizontal line test. Any horizontal line you draw, bear with me, horizontal-ish, is not going to touch that graph more than once. So this one is one-to-one, and it would have an inverse. So sometimes we can force functions that normally wouldn't have an inverse to have an inverse by just restricting their domain. And mostly this is done with parabolas, for example, like x squared. So if we think about the function f of x squared, and we restrict its domain to just being positive numbers, so we're going to make the domain be 0 to infinity. So we're just going to look at the right-hand side of our graph. So if we look at a parabola, we get rid of the left, so this guy's gone, right? No more of that, and we only use the right-hand side of our graph. So we've restricted the domain. We've said we only want this function for 0 and more. So then we think about this, we will see that now it does pass the horizontal line test. So the range of our restricted domain is also 0 to infinity. And when we switch our domain and range, we can see that the square root of x would have the domain 0 to infinity and the range 0 to infinity. So if you need an inverse function for a function that doesn't always have an inverse, you can restrict the domain down to make it work for specific applications. All right, so what we're going to do now is we're going to step up our algebra just a little bit, and we're gonna check things if our inverse is algebraically. So this uses quite a bit of skills that we've learned recently. We need to know what inverses are, and we need to know function composition. So if you take two functions that are inverses and you compose them with themselves, you should always get back to the independent variable. So if you take f of g of x and their inverses, you should always get x. And likewise, you should get g of f of x would always give you x. And this should make sense because if I take g to some value y and f is its inverse function, f would take y back to x. So you would always end up where you started from. So if you start at x, you should end up back at x once you've applied a function and its inverse. So we're going to do this problem together. This one's a little bit harder algebraically than some of the stuff we've done so far. So the first thing we're going to do is we're going to find its inverse, and then we're going to check to make sure that they're inverses by composing them. So step one, let's find the inverse of f of t. So I'm going to first write y equals 3 over t minus 1 plus 5. And now I'm going to switch t and y and solve for y. So the first thing I need to do to isolate this y variable is I need to work from the outside, and I'm going to subtract 5 from each side. So that gives me t minus 5 equals 3 over y minus 1. Now I need to get that y minus 1 out of the denominator. So I'm going to multiply both sides by y minus 1. Kind of squishing it in there. So the left-hand side looks like y minus 1 t minus 5 equals 3. And now I want to keep isolating the y, so I'm going to divide both sides by t minus 5. Just keep moving things around. And that gives me y minus 1 equals 3 over t minus 5. And finally, I just need to add 1 to each side. Oops. So y equals 3 over t minus 5 plus 1. So there's my inverse function of t. So I did the first thing. I found the inverse function of t, and now I'm going to verify that these algebraically are inverses. So that means I'm going to take f of f inverse of t, composing those functions, and hope I get t. That means I did it correctly. So let's do that. F of f inverse would be f of 3 over t minus 5 plus 1, which is going to be equal to 3 over, and now everywhere I see a t, I'm putting in 3 over t minus 5 plus 1 minus 1 plus 5. So that was a pretty tricky function composition. Let's just remember I substituted this whole business in just for my t, okay? And so let's keep going. We can simplify. Well, the plus 1 and minus 1 cancel each other out. So that gives me 3 over t minus 5 plus 5. And remember, when I divide by a fraction, that's the same as multiplying by the reciprocal. So if I think about this as a fraction, I have 3 divided by 3 over t minus 5. I'm just going to do that in a little thought bubble after the thought here so you can follow my algebra. If this is a little rusty, I have 3 divided by 3 over t minus 5. And that's the same as 3 times t minus 5 over 3 using my division of fractions rule. So this becomes 3 times t minus 5 over 3, and I still have this plus 5 along for the ride. The 3's cancel each other out, and I get t minus 5 plus 5, which is t. So I'm happy. All right, so I found the inverse of f of t, and I verified that if I compose those two functions, I got t. You can practice now if you want to compose them the other way. That would be a great opportunity. I'm not going to do it in this video, but it'd be great practice for you to make sure that when you take f inverse of f, you also just get t. All right, that's it for inverse functions.